All right, in this video, we are going to go through the setup of a VESC-based one-wheel board, and this is a general setup. This particular board is a DIY with an 84-volt battery using a hypercore motor. However, the general principles should apply even to the superflux motor, and I'm fairly certain the Cannon core motor for a float wheel. There will of course be different things to optimize the performance of either motor. However, this should generally cover the overall setup to achieve a board that functions and rides relatively normally. Now, this is only going to be a software setup. We're going to go through setting up the actual motor controller from the motor itself to the float package and the balance tuning. And within this, there is going to be a bit of information that I think is necessary to understand regarding your particular battery setup in order to input proper values, both for the information that VESC tool or other apps may give you in terms of telemetry, but also in making sure that the board functions properly with the voltage range of your battery. Just some context, this is the board that I've been riding, and I'm going to go ahead and update the firmware because I haven't. And this setup really only applies to a device that is already functional. So that's a device, whether it's a DIY or a full custom build or a float wheel or a fun wheel using a superflux, assuming that all the parts actually do work and none of the parts are defective. This thing's been working fine for several months, and so this is happening on a known functioning board. If any of your parts are broken or fail, this video will not cover that. That's an entirely separate realm of troubleshooting. This is purely just a software setup from top to bottom to get this thing on the recent firmware and getting it functioning relatively normally. And so when you're doing this, there are a number of ways to do it. If you have an XR shaped board, which this is, you could lay it on the side rail for the motor setup. Some folks use a milk crate. This is on a set of very large urethane skateboard wheels that I use as work stands. Anything so long as the motor itself is free spinning and is not contacting anything which would be dangerous. You wouldn't want anything to get lodged here and to get launched or to cause some sort of unsafe situation. So whenever you're doing motor setup, you want to make sure that the motor is not blocked by anything that could get caught. This is currently off. We will now turn it on. VESC tool is open on an Android device. I highly recommend, if you are going to own, tune, set up, operate VESC-based PEVs, whether that's a one-wheeled board or an e-skate or whatever, I do recommend having an Android-based device, even if it's just for the sake of using VESC tool. The reason is, in a board like this, getting to the USB port on the VESC in here, by the way, is a little Fokker made by Shaman Systems, version 3.1, and it does have onboard Bluetooth. This board also does have an external Bluetooth module that I connected specifically to get better connectivity with my iOS device. Bluetooth connectivity through all this stuff between this VESC and VESC tool on the iOS is very shaky. The connection drops. It's not a good way to set up a board because if the connection drops while you're writing settings, you may have to redo things. It may cause errors. There is a much more reliable, stable connection using the Android version of VESC tool. And so this is a very old device. This is a Pixel 3 and it works fine. It's only used to run VESC tool, and it would be a good idea to have an Android device to run VESC tool, even if it's just a cheap mobile that has nothing else on it except for VESC tool. So that's what we'll be running it on. This is now on. We're going to scan. Usually you'll be able to recognize, especially if you don't have a lot of VESC-based devices around you. And so these are the two that are in the board. Clearly it shows little Fokker built in. We're going to connect to that one, and I'm not going to connect to the external one. I'm just going to connect directly to the Fokker. And so you would connect and then select the VESC that you know, or rather the VESC-based ESC, that you know is in your board and is on. This is showing me a warning that it has old firmware because this is on 5.3. And so what we're going to do now is we're going to just flash the current firmware. And I'm showing you this because in some cases with a VESC-based device, flashing or reflashing the firmware can fix issues that you may otherwise have no clue how to fix. VESC can be buggy, and so you may be running into issues, whatever the device may be, that you just can't quite pin down a real fix for, and in many cases simply reflashing the firmware and going again from scratch can alleviate a lot of issues. And so we're going to reflash the firmware, and I'm going to try to do this entire thing on the mobile device and demonstrate how to do that. And so we will go to the Firmware tab, and you'll see the hardware version up on top. Underneath that, firmware, it's the VESC default. Some VESC-based controllers from some brands do require custom firmware. So there are some VESCs in a couple of Eastgates that I'm working on that require custom firmware. And if they do, the maker of the VESC should tell you, and you should not update it from the standard menu. You would go to the custom file, which is something you should very much just do on a Windows PC. And you would have to select their custom version of the firmware. The little Fokker, as far as I know, all of them don't require custom firmware. You can just flash it from the default tab, and it's already marked to take the hardware specific version of the firmware. And so this, for a Fokker and for, I think both the 3.0 and the 3.1, far as I have seen, I believe the VESC inside the float wheel is a clone of a little Fokker 3.0. And so it uses a different IMU than what's in the 3.1. However, it should still be flashable from the default page of the firmware tab. And so this is default. We will now click or tap upload. And by the way, at the bottom, it shows you the firmware version 5.3, the hardware, little Fokker v3.1. And so we tap on upload, not upload all, because there's only one VESC. In an Eastgate, that is 2 motors. It's usually a dual VESC, and so you want to update all of them. But in this case, you're only updating one, so we're uploading one. And it gives us the warning. VESC tool has a lot of warnings, and so this also explains why sometimes when you just have an issue and you know your parts are working and you can't troubleshoot the issue, a reflash can sometimes just fix it. It wipes every single setting. And so I haven't wanted to do this because this board has been running fine, but here we are. And so I tap OK. And now it is going to erase the bootloader. It uploads a new bootloader. And now it is going to upload the firmware. Over USB, this is much quicker, but this seems like it's going at a decent pace. The way the firmware uploads work is that it uploads it from your device to the VESC's memory. Once it's fully uploaded, it then runs a checksum, and then it reboots it, and it flashes it during the reboot, and then it boots back up. So it's not actually writing the firmware right now, it's just uploading it to the memory on the VESC, and then once that's complete, it'll run through a boot cycle and then actually flash the firmware, which is why it then will pop up a warning for you to wait, because you don't want to shut the power to it while it's writing the firmware, because that would be a problem. This is also why it's a good idea to just go ahead and get a cheap single-purpose Android device if you don't want to go through USB, because the connection dropping now has in the past, not often, has in the past, bricked a VESC, which then requires the use of an ST-Link, and then you have to flash the firmware and the new bootloader directly, and that is something that if one can avoid it, one should avoid it. And so that's why things like this, I will just do it on an Android device. All right, so the upload is done. It gives us the warning that the upload is done. It should reboot automatically within 10 seconds. I usually give it about 20, and then I scan for the device again. And so we'll tap OK. We've waited long enough. Hit scan up on the top right, scan BLE, and they show up again. So that means that this is on, and we will connect to the little Fokker built-in Bluetooth. And now on the firmware tab, it shows that firmware is 6.2, and so that's the current firmware, and now all the settings in this board are gone. And so we are going to start from scratch. All right, so we're going to go over to the Start tab. This is the main screen that you see on the mobile version when you first open up VESC Tool and connect. It shows the button for disconnect because we are connected, and you can see some RT data. This is all going to be wrong because it's not set up properly. However, if you scroll to the top little dot, the first menu, you can see your battery input voltage. So right there, it's at 75 volts. This is an 84 volt battery, and it's roughly about half-ish. And you have your motor temperature and your VESC temperature. So temp MOS is the temperature of the MOSFET. Temp motor is the temperature of the motor. No fault codes, that's all great. The IMU is not set up, so it's not reading anything. And so that's your information. But we're gonna go back to the start. And before I actually do any of this stuff, we're gonna talk about battery stuff, because knowing what battery is in your device and being able to figure out some numbers is, in my opinion, very important to setting up your device, inputting proper values, and understanding what those values mean in terms of how it works. So, lithium-ion battery in here, using lithium-ion cells. This is going to be for demonstration. I have a stock XR battery right here, and so we're going to start with some math. For lithium-ion batteries, regardless of the configuration, I find it useful to think of it in terms of a single cell. When we're talking about voltages, I like to think of things in terms of a single cell. And there are only 4 values, really, that you need to know and internalize for a single cell. And from there, you can figure everything else out. First, and I will have this in an article that I will link to in the description below, explaining that in more detail. So, 4 values. First one, full. A lithium-ion battery cell, a single cell, full is 4.2 volts. That's what it charges to. That's when it's full. Going above that is bad. Next value is nominal. It's called nominal because that is what cylindrical lithium-ion cells are named as in terms of their voltage. It's a 3.6 volt cell. You don't really use it unless you want to think of 3.6 volts as being halfway. That's about halfway through a charge, more or less. Then you've got 2 empty values. Empty regular, which is 3.0 volts. When you're setting the low battery tiltback or pushback of your board, you base it off of, generally, 3.0 volts. Try to think of all your battery cells as being empty at 3.0 volts. So that's empty regular. This is on cell data sheets what empty actually is, 2.5 volts. Generally, you don't want to drain a cell that far because you stress it more than you need to. It's not dangerous, but it does increase the wear. And so you can reduce your cycle life by discharging down to 2.5 volts per cell. And so that's not really recommended, especially because below 3 volts, there's simply not a lot of usable energy. The drop-off is much steeper, and so you're better off, for the sake of cycle life and really usable energy, to just consider 3.0 volts as empty. There's wiggle room, but if this is really new information to you, stick with thinking of empty as 3.0 volts, and I consider that empty regular, but empty is 2.5 volts. Now, for your particular battery, you can simply take those values and multiply them by the S count of your battery pack. What is an S count? It's how many single cells, or groups of cells, are placed in series. Here's what I mean. This is a stock one-wheel XR battery. The configuration is 15S 2P. And that first set of information is your S count, 15S. That means that there are 15 cells in series, placed tail to tip, front to back, positive to negative. And so you have 15 of them, which means if you want to find out what full voltage is, you take 4.2 volts, multiply it by 15, and you get 63 volts. So this charges to full at 63 volts. And you take that pattern and you just use it for all of these other values. Nominal 3.6 volts. If you multiply 3.6 volts times 15, you get somewheres about 54 volts. And that's why this is called a 54 volt pack, because that's what they name it, via the nominal value. Empty, 3 volts times 15 is 45. Did that mentally. 45 volts. So 45 volts is empty for this battery. And you can take that type of operating math and apply it to whatever battery configuration you have in your board, which you should get from either whoever made your battery or whoever made your board. If you made your board and your battery, this should all be nothing new to you. So in here, there is a 20S battery, which means at full, it charges to 20 times 4.2 volts, 84 volts. The nominal voltage, what one would call this outside of this sort of operating land, 3.6 times 20 is about 72. What is empty for this battery at 20S? 3 times 20, 60. 60 volts is where this thing pushes back and tells me that the battery's empty, even though empty would be 2.5 volts times 20. So you do have to do some math, and it's important for you to be able to do this simple math just so you can check your values and know what values to put in here in order to make this thing function properly. Because if you have a 20S battery, which is what's in here, and I believe is in the float wheel, and you start setting your voltages for a 63 volt battery, for a 15S battery like this, it's not going to work right and you're not going to have a good time. So the battery pack voltages based on these 4 values is something that is really important to internalize, so that way if you have one board with a 20S battery like this or a float wheel, or you have another board, maybe you have a DIY or a custom that somebody made with an 18S battery or a GT with an 18S battery, you want to be able to take these values, multiply it by the cells in series, the S count, and then go from there and get the values that you need. What we're going to do now is we're going to do the very first thing that you generally do when you're setting up a VESC-based device, such as this, and we're going to run motor detection. What motor detection does is the VESC itself runs power through the motor in a couple of different ways, and it uses what it finds by running power through the motor to understand more about the actual way that the internals of the motor are wired. And so there is a wizard for that, and it is below the connect-disconnect setup motors. And I'm going to give you a bit of information as we go through it. Try to keep it basic, but we're going to tap on setup motors. It's going to process and load the wizard. Load default parameters. It always asks this. I tap no. And then I tap EUC. You have a button there to override stuff. In this particular case, I don't. I leave it at EUC and I tap next. And then it's going to give you a bunch of different kinds of motors. Mini outrunner, small outrunner, medium outrunner, large outrunner, all these other ones. This is an outrunner motor. What that means is that the part that turns is on the outside. An in-runner motor, oops, ignore that. My bad. Let's go back here. An outrunner motor has the turny bit on the outside. An in-runner motor has the turny bit on the inside. So if this were an in-runner, we would be clamping stuff to the outside and then the axle would spin. That doesn't happen here. The outer bit is what turns, and so this is an outrunner motor. It's larger than an escape motor, which, hold please. It's larger than an escape motor, which is right here. This is also an outrunner motor, because we clamp onto this bit, which is the motor plate, and the outer bit turns. And rather than having an axle run through, the axle runs through one area, and then that's what turns. This is also an outrunner. This is what one would consider a medium outrunner, because this thing weighs about, I'd say about 500 grams, and medium outrunner is about 750, but according to this, a small motor, small outrunner is much less. You want to be able to add that information or select that appropriately, because if you don't choose it right, you could damage your motor because it'll send too much power to it. And so we're going to select a large outrunner motor. We are then going to go to Override, Advanced, and it's going to give us some options. Now, the values we're going to change here, there are only 2 of them, and they apply to the hypercore. They also apply to the superflux, and from what I can tell and what I was told by Surfdado, who looked closely at the previously published video on setting up the float wheel, the values for the Cannon core appear similar to the hypercore, and so it stands to reason that this will apply as well. And so first thing we're going to change is motor poles. This has 30 motor poles, the superflux has 30 motor poles, and I'm fairly certain that the Cannon core has 30 motor poles. We're going to change the sensorless ERPM value from 4,000, which is the default, to 2,000. And that is the ERPM limit where it changes from using the Hall sensors to not using the Hall sensors. And those are the only 2 values that we're changing right now. And so once those are changed, we will hit Next. It will give us another warning to make sure that we chose the right figures for the motor, so that way we don't damage it when it runs power through it. So we click Yes. And here it's going to ask us for battery information. This relates to what we talked about before, and this doesn't really affect the performance of the motor. What this really affects is the stuff that shows up on the real-time data screen. So if you're looking at like your battery percentage or your watt-hour consumption, this stuff is mostly for those areas. However, since we're here, it's a good idea to just fill it in with the information that relates to the battery you know you have. So, battery cells in series, we just spoke about that. This one has 20. If you have a float wheel, probably have 20. This one has 20. If you're using an 18S battery, you would put 18. And yeah, you should know what the S count or the series count of your battery is, either because the person who made your device or your battery will tell you what it is, and that's the configuration you would find on it. So a stock XR battery would be 15 cells in series, because it's a 15S battery, is a 20S. I also make 18S batteries, and you would put 18S there. Battery capacity, I'm not going to go over this in much detail, but again, the maker of your battery or your device should tell you that. The long and short of it is, the battery configuration looking here, it says 15S 2P. 2P means that there are 2 individual cells making up a single bigger cell, like a parallel group. That's what the P is for, parallel. How many cells are in parallel? To get the actual capacity of the pack, you take the capacity of a single cell and you multiply it by however big the parallel group is. So in here, 15S2P, that's 2 cells in parallel. Each of these cells is 3 amp hours, so that's 6 amp hour capacity. Also says it right there, 6,000 milliamp hour, so 6 amp hour capacity. This has a 5.6 amp hour capacity battery. I believe the float wheel has an 8.4 amp hour capacity battery. The customs that I make that are 18S have a 10 amp hour capacity. And so you would find out what the amp hour capacity is of your battery, and you would stick that in the part that says battery capacity. This already says 5.6 amp hours. That is correct. And so I don't have to change that in particular. Below that, advanced. Leaving this unchecked will leave it at default. You can do that for now. I'm going to change it because I know the battery specs for this. And so also in the article that I'll link to in the description, I will have some figures that I think will be reasonable to put here or in the current limits and motor configuration later, but I will have some figures and I will denote where to put them. So for now, I'm just going to do what I know the battery is going to be used with. So battery current regen, that's your regen braking, that's how much power it's going to stick back into the battery when you're braking. And so I set that to -25. I'd say -25 is pretty decent. Battery current max, I put this at 40. 45 is probably fine. I'll put it at 45 for this. I know it can handle that. By the way, for the battery current and the battery current regen, what I do not recommend you do is to take the current figures from like a cell's data sheet and just multiply it by, your parallel group size and put that number in there. That's not a good idea. So for example, if you have a battery pack made of the Molicel P42A or the Samsung 40T, and those cells, if you look them up, if you just Google them, it says it's a 35 amp cell or a 40 amp or a 45 amp cell. Do not take that, double it by the 2P figure in your battery configuration, and then assume that you're going to set your battery current to 90 amps. Don't do that. Do not do that. It's not a realistic figure. Not that you would ever actually pull that many amps from a device like this, but just don't do that. That's not a realistic figure at all, and that number ignores all of the context of how, for the most part, these cells are being used. So don't do that. Just don't do that. And so that's what I'm going to put, and I think that's reasonable, and I think that offers exactly the kind of performance one needs, and so that's what I'm going with. So we're going to hit next. Gear ratio. There's no gear ratio because it's a single wheel on a single motor, so it's direct drive. Wheel diameter. If you don't want to measure your tire at its inflation pressure, you don't have to. I recommend you do by just like taking two sticks and having them point out here and then sticking a ruler there and measuring the millimeters of your actual tire diameter. That will give you more accurate speed figures in the real-time data tabs and probably in flow control if you're using that app. You don't have to, you can just guess. If I'm trying to be quick with it, I'll just add a 2 in front of wheel diameter and assume that this is about 283 millimeters. This in particular, I think, is 288 millimeters? 287. It's something like that. This is close enough that it's not going to be so outlandish of a figure in terms of speed. It's not. I'm not going to be going 10 miles an hour, and it's not going to show me like 30 miles per hour. So if you don't want to measure it and you want to measure it later, you could just put that right there, and that will technically work. Motor pulls is still at 30, and then we're going to tap on run detection. That's when it's going to do its thing. So it might default to having detect all motors over CAN bus. I'm going to unclick that because no motors are over CAN bus. It's a single VESC with a single motor. So I untick that and click OK. And now it's going to do stuff. Now it's detecting Hall sensors. All right, and so it's going to give you detection results. It'll say success, even if it's not successful. It sometimes just says success and then gives you crazy values, but these values look relatively normal. I will post the values in the article, linked in the description, for what I got here, and I will also link to a PEV.dev article with hypercore and other motor information to sort of see if what you're detecting is normal. Because if you don't have any other spare parts to troubleshoot with and you have no experience troubleshooting stuff and you don't know if your motor is actually good, then it can help to have values from motor detection to compare it against. So if one value is wildly different from what everyone else with the same motor is getting, that's a good sign that something is wrong with your motor or something is wrong with your VESC. So I'll post these numbers, and again, I'll post a link to an article with known good values and some more information on that. This looks normal. It's detecting the Hall sensors, and so we'll tap OK. And then it pulls up this thing for you to test the direction of your motor. This is important because if your motor direction is not correct, then you'll have some very bad experiences. So you tap forward, and it should rotate in the direction that you would be traveling forward in. If you tap reverse, then it should travel in the direction that you would be reversing in. That's about it. If it doesn't, and it's backwards, then there's a toggle here for inverting your motor direction. So now if I tap forward, it's going backwards. And if I tap reverse, it's going forwards. So I didn't need to do that, so I will untap that toggle, and I see here that it is now going forward, and it is now reversing. By the way, if you're tapping this and it's not actually moving and you got a whole bunch of weird noises happening, the most likely cause for that is that you have float package installed, and so you should uninstall it or disable it before you do this. And keep in mind, this whole video started with an entirely fresh reflash of VESC firmware. So there's no float package. There's nothing on here. It's totally blank. And so that is what should happen if you just do motor detection from scratch. No float package. If you have your float package installed and you haven't disabled it, it's going to do weird things and those toggles are not going to work. So that's that. So now I'm going to hit finish. What I like to do also is go onto the controls tab and just check to make sure it's actually going to run. It's on current. It's going to send 3 amps through the motors and it's just going to run it. So I hit set forward. Brake and reverse, forward and reverse. If you want to have some fun with it, you can up the current just to see how it responds at, let's say, 20 amps. Woo! Reverse. Brake. Obviously be careful. Probably shouldn't do what I was doing. I was having some fun. But don't do that, you could get hurt. But that is a way, if you leave it at default like 3 amps, like it is normally, then you'll be able to see if your motor's actually functioning. And I do this on e-skates too, just to make sure that the detection actually makes the motor work. Now, this motor is now functioning, it's working. It's not optimized because there are a couple of values to change, but it is now working. So we're going to close this, and then we're going to go into the motor configuration area, and we're going to change a few of the values that are more or less going to help optimize this particular motor. And they do, in some cases, also carry over into motors like the Superflux, and I'm guessing the Hypercore. If there's more, better, updated information specifically, those values are going to be pertinent to this Hypercore, which is a future motion motor. However, those changes also, in part, can apply to the Superflux, and it stands to reason the Canon core. If there's updated information that I get after making this video, I will go ahead and just post that in the link below and likely do a more specific video on setting up the Canon core. But more or less, generally, this motor is now functioning. And so there's a difference between functioning and optimizing. All right, so in the motor config tab, there are 2 steps to do. One is the important critical stuff to make this motor continue to work properly. And then there's the other stuff for optimizing for a specific motor. And the optimizing part is really particular to each kind of motor, whether it's a Hypercore like this, a Superflux, or a Canon core. And those values that optimize it will also be in the link below, whether it's a pev.dev forum thread or a part of the article that I'm linking for this with more information. The optimizing really just makes the motor work better, especially under higher currents, such as hard acceleration and braking. However, what we're going to do first now is setting the values needed to make sure that the motor part of this device functions properly. And so we're going to start when you hit the motor config tab. You're right in both the general tabs. There are 2 drop downs you'll find. And so we're going to stay in the top drop down, general. Second drop down, we're going to go to current. And this has to do with motor amps. And when you run through motor detection, it detects how much current the VESC believes should be run with the motor. And right here it detected about 55, both on accelerating and regen braking. And that's a bit low, and so we're going to up that. What I usually use is, I'm just going to select the whole thing if I can. It's hard to, all right, we're just going to go ahead and delete that. For a hypercore, I think what works best is somewhere between 90 to 110 amps. If you go above that, you're going to have to work a bit harder to remove some of the motor cogging and crunching that happens at very intense braking and accelerating, mostly braking. But and some folks run higher current than that, and that's fine. You just have to do a bit more optimizing. And so I find that with about 95-ish, in this case, let's put 100 amps. And I will mirror this down here for motor current max brake. That's the strongest braking strength, negative 100 amps. I find that between 90 to 110 is a good place to start for a hypercore. The superflux, without a lot of optimization, can handle much higher current because the stator is much bigger. There's a lot more material there. It heats up much less. But for a hypercore, which this is, I find that 100 amps, I think before this I had it about 95. That's a decent range to start. And if after you're done, you feel like it could be a bit more powerful, you can slowly raise it up. But I'm going to leave it at 100. Absolute maximum current. This means that if it, I'll explain why in a second. Absolute maximum current is the absolute maximum current that the VESC will allow to be detected at the motor. And there's some granularity, there's some details as to how it measures it and why it would reach a higher current. But that absolute maximum is really the brick wall. If this motor, or rather the VESC detects more than this through the motor, it will throw a fault code and it will shut the motor off. So you want that to be pretty high, usually about 150% to 200% of what your motor current max is. And so 82 amps is not going to cut it. We're going to put it at 180 amps, absolute maximum current. And then that should put it far out of the way. However, if the motor is cycling 180 amps, we will throw a fault code and the motor will shut off. The rest of these, right below those current values, you don't really need. And so we'll go down to, you see that blue tab, battery. This we already set when we were doing motor detection, and so those values are there. Battery max current 45, battery current max regen negative 25 amps. I will leave reading in the description below and some more information on battery limits and why I set them the way I do. However, those two numbers will pretty much work for almost any of the batteries that you're likely to use in most VESC-based boards, except future motion batteries. So if you have a DIY build or a converted board or a refurbished board using a 15S stock XR battery or a pint battery, those numbers won't work. For the stock XR, leave it at 30. For the pint, I'd say leave it at 20. For a CBXR, I'd leave it at 30. And even for a GT battery, if you're doing a build with like a GT battery, an actual GT battery, I'd probably put that at 32. As in 30 as well, not 32. So these numbers are fine. 45 current max, 25 current max regen. For like a custom aftermarket battery, I'm sure that's fine on the float wheel. They might recommend higher. You can do that. I think these numbers are fine, but stock XR battery, 30. 30 max current. Don't go higher than 30 amps. That would be bad. So there you go. The rest of this stuff, you can leave it alone. Once these values are good, you've entered them, hit right, and then you'll notice a little blue thing there. After you do the values on a single page of a dropdown, hit write. That's writing it to the memory of the VESC, and then you can move on from there. So we've done current. Next place to go, we're going to go down to BMS. This only matters if you have a VESC connected BMS. This thing does if your build has a ENNOID X-Lite or other VESC connected BMS. Do this. Uncheck state of charge, uncheck overtemp, and bring down SOC limit start to 0. And just for good measure, I would raise these temperatures up to like 70 just to get them out of the way. So all these values are doing is effectively disabling information from a connected BMS, like an ENNOID X-Lite, from doing anything to the motor. Because what this can do is if the battery is too hot or the battery is at a low amount of charge, and as per the BMS, so if the BMS thinks you're at 5%, this tab controls the motor current, which means that it will drop out current and it will drop you. This needs to be disabled if you have a VESC connected BMS. So like an ENNOID X-Lite. If you've got that and you're connected to your VESC, that needs to happen so that way your BMS doesn't tell your motor to shut off. That would be bad. You can use BMS data if you have an ENNOID X-Lite, but you want it to inform tiltback, pushback stuff to signal you, not to just turn the motor off, because that would be dangerous. So that's why I uncheck those and I bring SOC limit start down to 0, and that's at 0, and all that stuff is 0. And then you write. That just means that the BMS information won't affect the motor, which would be bad. All right, so that's that tab. And now we're going to go to a very important part. This is really important, super important. So we're still in general on top, the second drop down, voltage. So motor config, general, voltage. This is super important. So these are battery voltage cutoffs. What the battery voltage cutoffs do is, depending on your battery level, the voltage that your VESC is seeing at your battery, it will inform the motor. And that is not what you want it to do. Anything to do with your battery percentage or your voltage, anything that's a low battery or high battery, you want it to translate into pushback or tiltback to signal you, not to shut the motor. So in motor config, general, voltage, these cutoffs shut the motor, which is bad. So you want to make these at a value where you won't reasonably reach them. And so here we see battery voltage cutoff start and battery voltage cutoff end. So cutoff start means that it's going to start throttling back the power at the motor. So it's going to make the motor weaker and you'll lose acceleration. But you need acceleration to stay balanced. Battery voltage cutoff end means the motor shuts off. Some people mistakenly, assuming that's a word, set this to 3 volts per cell. Going back to earlier on those 4 important figures. So empty regular, 3 volts per cell. Some people set this to 3 volts per cell or thereabouts. That's bad. Do not do that. That will hurt you. The reason why is if you set your battery cutoff voltage or your battery voltage cutoff to empty values, when you hit tiltback to signal low battery, the moment you hit it, if you push into it at all, it will shut the motor off because your voltage will drop to the levels pointed out here and it will just shut off the motor. So what these are really for are to keep your board or your device from draining the battery beyond an unrecoverable state. So what I do is I set the cutoff start to about 2.3 volts per cell, which is well below empty, and the battery voltage cutoff end to 2 volts per cell, which is really below. Have I hit those values before? Yes. What happened? The motor shut off. It dumped me. I was going very slow anyway. And then, since the load was removed entirely from the battery because it shut off, the battery voltage bounced back up and settled at about 2.5-ish volts. And so it was there at empty. So you don't want these in a place where it could hurt you, and so you want it well below your tilt back or your pushback low voltage. So we're going to do cutoff start. So this is a 20S battery. Let's get the paper. We're going to do some math. All right, so we have a 20S battery. We want this to be below that. Let's say that battery voltage cutoff start. Let's say 2.3 volts per cell. This is a 20S battery. I'm going to do 2.3 volts per cell times 20, which is 4 to 6 volts. And so I will put battery voltage cutoff start at 46 volts. Okay? Battery voltage cutoff end. Let's say 2 volts per cell times 20. Battery voltage cutoff end. 2 volts per cell times 20 is 40. So we'll go here and we will put 40 volts. So these are the battery voltages that a 20S battery will actually start to shut the motor off, and that is below pushback or tilt back voltage. That is important. You do not want those at 3 volts per cell. You don't want it near that, and I don't even want it near 2.5 volts per cell because this will drop you right at pushback if you do that. So here for a 20S battery, 46 volts start, 40 volts end. That's what I put. Right. Confirmation, fantastic. Okay, and now we're done with the general tab on top. So now we're going to go to the FOC tab on top, and we're going to start at general. So now we are slowly entering the realm of optimizing the settings for the motor, and these will become a little bit specific. So what I'm doing here, I'll start with things that will apply also to the superflux, except for a couple of things, and I'll cite those. But this is another area where you really want to go into the description, click the links in there with the extra reading, and find out what values have been found to optimize for a particular motor. So this is a hypercore. If you have a superflux, a lot of this will still apply, and I'll mention that. If you have a Cannon core, chances are a lot of this stuff will apply. However, the exact values, you should absolutely do the reading to look them up exactly. And so we are under FOC, General. Don't touch this. Sensor mode Hall sensors, we want that. So motor resistance for the hypercore, as per the article linked in the description below, I'm going to raise this to 100. If I can just get there. 100. For the superflux, what I do is I increase motor resistance by 30%. So that's what I do for the superflux. So I take the value that's been detected, I times it by 1.3, and then that's the value I put there. For the hypercore, you'll find in the link in the description below, the pev.dev article, that they mention a value between 90 to 110. I find for this particular motor, 100 works well, and so that's what I'm going to do. All right. Down here, observer gain. That's the last one there. We're going to take that value and we're going to cut it in half. So anywhere between 0.75 to 0.85, something like that. This is reading at 1.28, so 1.28 divided by 2. So observer gain for the hypercore, it seems that it works best to set the observer gain to 0.75 or so. For the superflux, whatever detected value is there, which is usually about 1.4-ish, cut it in half. So for the hypercore, I'm setting that to 0.75. For a superflux, I would just take that value and cut it in half. All right, so that's all we're going to do here for now, and we're going to hit right. There's one more thing you can do. Now, there's one more thing you can do if you're using a hypercore, and that is reduce motor inductance. There are some different values you'll find on the forums and on posts in the Facebook groups. This one in particular detected at about 233-ish, and so lower that. In this particular case, I've had good luck with a value here for this hypercore at 200, and you'll find a variety of values. Sometimes it's 198, thereabouts, but lowering it to around 200 seems to do well for the cogging and crunching sound under hard braking. If it doesn't, you can return that back to its prior value, so make note of that, and you should be good to go. And that is about it for this, so we will go ahead and write that. And again, this is something where you really want to click the links in the description below and look at the values that other similar setups have gotten from detection and the changes that have been made for optimizing the performance of that particular motor. All right, so onto the second drop down. What we're going to do now is we're actually going to go to the Hall sensors, and we'll see a familiar value from detection, sensorless ERPM. We should have changed that from 4,000 to 2,000 in the motor detection wizard. However, if you didn't, now would be a good time to make sure that sensorless ERPM is at 2,000. And right below that, Hall interpolation ERPM, you want to lower that to 200. And this is something that I do on the hypercore and on the superflux. And so that is an important value to note. Sensorless ERPM 2000, Hall interpolation ERPM 200. So we write that. We're now going to go to advanced. We're still under the FOC dropdown. And the zero vector frequency. That's basically the switching frequency for the VESC. And so a couple of things can happen from it being at 20 kilohertz. No sense getting into the nitty-gritty of it now. However, most folks have had good luck raising this anywhere between 25 to 30 kilohertz. In this particular case, I'm going to put it at 27 kilohertz because I've had good luck with that, and then I'm going to hit right. Now, after setting your zero vector frequency, what I do for this particular motor, which is the hypercore, is I change the observer type, and you can find that same place. So we're in FOC advanced, same place, scroll all the way down carefully, you don't want to change values, and you'll see observer type. The default observer for VESC firmware 6.0, and I think everything after, so it started in 6.0, and so this is 6.02 or 6.2. The default one is this one, MX Lemming Lambda. For hypercores, I set it to Ortega Original. For the superflux, I don't change it. I leave it at the MX Lemming, whatever the default is, and it works fine. However, for the hypercore specifically, I will change it to Ortega Original. And then all the other changes that I do for this, the value adjustments, that all stands. And so I have found that in some cases, the hypercore motor sounds or feels or behaves oddly with the newer observer. And so I imagine it's just a motor-specific thing. So for the hypercore, for future motion motors, I will change the observer to Ortega Original. But again, for the superflux, the Fungineers motor, I won't. I'll leave it as default, and I'm not certain yet what the Cannon core motor would work better with, and so that will just have to be tested. And chances are, if it's anything like the superflux, the default observer is going to be fine, but for the hypercore, I find that Ortega Original is a better observer. Next, we're going to go to field weakening, which is disabled by default. Field weakening is a way to increase the top speed of the motor per the voltage of the battery. By default, it's disabled, and the general consensus of a decent place to start with field weakening is to add or raise the field weakening current max to 30 amps and the field weakening duty start to 60%. That's a good default place to go, and you don't even really need that unless you're actually looking for extra top speed. Some people don't use field weakening. However, those that do, these are a good basic value to set. And again, link to the information that will describe why that is. So that's been done. We'll hit right. So now we're going to go to the start page again, and we're going to go back to controls. After all these changes, we want to make sure that this motor actually still functions and it's not just going to cog out and do weird stuff. And so we're back where we were. Forward. Reverse. Ignore the wobble. I've found that if the board's just been sitting there and you do that, the tire sealant that may or may not be in it just pools. And so when it starts turning very quickly, it just sticks in one area and just starts to wobble until you sort of even it out. So you can try that and then hit reverse. All right, wobble's a little bit less, but either way, that wobble is normal if it's just suspended on two tiny little posts here. But anyway, so we've checked that this thing still functions and there's no abnormal goings on with the motor. And so that's good. So I would consider this functional, and I would consider us done configuring the motor, which means now we're going to configure the IMU. So motor's done. Next step is the IMU. All right, now that we have the motor functioning and partially optimized for the most part, what we're going to do is calibrate the IMU, which stands for the Inertial Measurement Unit. It is a unit that measures inertia through several sensors. And so some of this is going to involve moving the board, some of it's going to involve making sure that it's level via pitch and roll. And so one of the tools that I think is really important to have is a simple bubble level with a flat edge. And so you of course can use a bubble level app on your mobile device. However, they don't really work as well as a traditional bubble level. And these are not very expensive. You can find one for $10 at a hardware store. And so these are really, really handy when it comes to making sure that your axes are actually level. So this looks flat. It looks like it's leveled, but it is not. So it's actually a bit nose up. And so I will shim that side in order to get this properly centered. And the same goes for the roll axis. These are standard flat XR foot pads. However, you might need to do a bit of navigating to make sure that you can get a flat seating area for this. But either way, it's also leaning slightly this way. And so when I get to that axis, I'm going to have to shim it to tilt a bit that way. Now, is that in a quarter of a degree, half a degree, 1 degree going to make a difference? It can. It can manifest in different ways with how the board rides. And so I do recommend just a cheap, simple bubble level. And so that, I think, is an integral tool for this process. And so we're going to go ahead and tap on IMU. The board is still on. We are still connected. Or you've taken a break and now we've reconnected. So we're going to tap on Setup IMU, which is below Setup Motors. We're going to do these in order. So the first one, IMU Configurator, it's very simple. You merely input what kind of device this is, and it should, up at the top, IMU Detector, under IMU Detected, True. So if you have an external IMU, you may not get a detection right away, and you might have to troubleshoot that. However, the little FOCer in here, which is one of the more common VESCs to be used in this application, has an internal IMU, and so it's detected. It does say in the IMU type that the internal timeout, or rather the internal IMU is timed out. I've seen that before, especially with older models. It doesn't really mean that you're going to have issues, and the newer little FOCers seem to all read the type properly. However, if it is detecting the IMU and that is true and it's green, for the most part, I haven't seen that present any issues going forward, and so we're just going to trust that that's going to work. Below that, IMU Profile Selector. Oh, by the way, before we do that, you can tap on Search for IMU, and it will look, and now we're waiting. Okay, and it's the same. It's still detected as being true. So below that, IMU Profile Selector, bottom right, Balance Skateboard, which is what this shape is. And so we'll tap that, and you'll see that the values change. And when you click Save, it will save those values to the VESC. It's a bit hard to see, but below this wizard window, there's a little blue line there. That was it writing and saving. That was the confirmation for that. And so that first button is now completed. Due to the internal timeout result in the internal IMU detection, you may note that the frequency value did not change to what it should have, which is 832 Hz. This will cause odd behavior due to sync issues with the sample rate of the IMU and the operational frequency of the float package. If you note that the frequency was not changed to 832 Hz in the first step here, you will have to change it manually. I recommend doing this after the rest of the steps, and so I will put that clip at the end of the clips for the IMU wizard, which we're just going to continue now. Gyroscope calibration. So this says to just leave it alone. It doesn't necessarily have to be level, but this is, in order to calibrate the gyroscope, going to need to just stay still. So we're not touching anything. Nothing around us is moving that could shake this, and so we're just going to leave it. And once those values there more or less stabilize, then we'll tap on save. And so the values are going to flutter. It's always going to happen, but they should more or less stabilize in a general area. And so we will just hit save. And that's about it for that. Now the next two, you're going to have to do a little bit of movement. And so accelerometer calibration. Okay, so here we go. We're going to move this, and we're going to take the board off of these stands. So if you have a milk crate that you're using to hold this, or some other work pieces that you have to hold this flat, you're going to have to remove them. And during the accelerometer calibrations, it's important to move the board fluidly, gently. You don't want to just take this off and drop it. You don't want jerky movements or really big movements where you're impacting parts of it, because those impacts will register falsely high values and you'll screw everything up. There is a button here to clear max. So if you do happen to just drop one side of it, or you hit something, or you impact an edge or whatever, and it gives you this crazy large value, you can clear the max and then continue on. But we're going to try to avoid that and very gently just move these work stands, as it were, away and not have any very large movements. And so the goal for these, you're going to do it on 3 axes, so 3 sides, and you're going to have to find them, which is exciting, is to get them to their maximum value, which is somewhere around 1. It might be 0.998, might be 0.999, might be 1.012, but around 1. Not -1, not 2, 1. That is what it should be looking for as the maximum value. And so here, the x-axis. So we're going to move it until we see it starting to go up. Okay, it's going down. That's not what we want. Okay, it's starting to go up. And so we're going to very carefully. All right, so it seems that the x-axis, it seems that this is the position it's going to be in. And we'll wait for it to stabilize. And we'll see if we tilt it a little bit more, if we got any more of the value to rise up. Going to do a little bit this way. All right, so it seems, oh, we hit 1. All right. A value of like 1,000th is not really going to be that big of a deal, so 999 or 1 is fine. And so that is where we're going to leave it, and we'll click Save. Now it wants us to find the y-axis, and we're going to do the exact same thing, but we're going to find the y-axis. And I think it's the nose, so we're going to bring it back, and we're watching the y-axis value to see if it goes up. We push the nose down. Okay, so yeah, it is the nose. So we're gonna, okay, I have to do this around the camera. Very carefully raise the tail, and we'll see that it is going up. Okay, so it seems that this is going to be where we want it for the Y value. This might not be the direction that your board needs to be for the Y value or X value or whatever. You need to very fluidly and gently find the direction that you need to move it so that the values move up towards 1. And so right here, We're seeing a max of 1.006. We're floating in that area. I'm just tilting it very, very slightly to see if I can get the value any higher. But it seems like that's about where it's going to be. And again, a difference of 1,000th is not going to manifest in any significant way. So this seems fine. So again, for this, or rather for your board, it could be that the tail is down and the nose is up. The board could just be flat, straight up, upside down. Any direction, you just need to make sure that it is on the Y axis. So we're going to click Save. And now I need to find the Z axis. This is the final one to do this with. And so for this particular board, I believe this value, it's just upside down. So I'm tilting it this way and I see it going up. And so yes, I think this is just going to be upside down. Careful. Okay. And so it is upside down. All right. I don't know if this looks a bit high, so I'm going to clear the max and let it do that again. No, it was fine before. Okay, so I'm just going to move it a bit, see if I get a higher value than that. And it does not seem like I am. No, it seems like 1.035 is pretty much where it's at. And again, a difference of 1,000th is not going to matter. So we hit Save. Okay, so that was the accelerometer calibration, and now we are done with that. We have one more button to go in the IMU wizard, and I believe this is the one that is going to involve it being propped up flat. And so there you go. Okay, so orientation. So roll angle. Okay, so we're going to have to level it out. So we're going to need, so this is the point where I'm going to put it back on these wheels functioning as stands. This is the point where you would put it back on a milk crate or, wood blocks, whatever you're using to prop up the board flat is what you're going to use. And this is where we're going to bring in the bubble level, because it is asking us to make sure that the roll and pitch axes are flat. So we're just going to go ahead and do that. These are my shims because I know this is not perfectly even. All right, so we're going to do pitch, which is nose to tail. And so this is slightly nose up. So we're going to shim the back a bit. I believe this is enough to just even it out. Yep, that did it. You might need to do more or less, whatever, but this is very useful to have. And so roll. It's gotta come this way. So we're gonna shim it with this 3D printer bed scraper. So okay. A little bit more. Oops. Too much. There we go. Okay. So the roll axis is level. Pitch axis is level. Okay. Back to the device. So calibrate roll angle, place the IMU on a flat stable surface with both the pitch and roll. Okay, so the roll offset, and now you'll see that the roll offset value has been changing this whole time, and it's settled there. And we know that the roll offset, we just measured it, is good. Yep, so this is roll. We'll click save or tap save. Pitch, that's the nose to tail. That's your lean angle. So we'll just check that, make sure that that's good. And we will wait for this thing to sort of iron out. And you'll see the pitch offset is about 0.5 something. It's fluttering, but that's fine. Okay, yaw angle. Okay. So the yaw angle is, I believe it's basically just steering. It's like this way. And so what we're going to do is we're going to lift the nose up to about 45 degrees, which we can do just by taking the rear holder off. If this were in a milk crate, you would just take it out of the milk crate and then put it on your bench or the floor, wherever you're doing this. And so we're going to lift it to about there. and the yaw offset will be approximately 90 degrees. And so we will save, and then that is it. Again, your yaw offset should be a multiple of 90 degrees, unless your VESC has a specifically odd mounting orientation. The flickering in the previous clip between 75 and 90 degrees was likely another symptom of the internal timeout error I got earlier, or just something else. However, it illustrates an important point. You will have to learn what value ranges are correct and adjust them to be within those ranges. Don't always rely on wizards as they are imperfect. VESC is usually imperfect, and it's usually best to manage imperfections rather than deny them. Now, after the IMU wizard and you're certain that you did everything right, and this is matching up and it's functioning, and it's all good, one thing I check is in app config under IMU. Usually it's in general when you get there to the app config tab, but I go down to IMU and I look at the sample rate. Now the sample rate usually changes once you select balance skateboard. It'll change the sample rate to 832 hertz, and that's what the float package runs on, 832 hertz. Sometimes it doesn't. And so if it doesn't, right here, if sample rate is not 832, then, well, I'm not going to go all the way down to 832, but hold. You want this to be at 832, and then we'll write that. And Excel gyro filters should default to medium, and so that will be fine. Now, you want that at 832. That is the same sample rate and frequency that because that's the frequency that the float package runs at, and if they're at different frequencies, this will feel weird. It'll act weird. If you've got like this weird kind of vibration thing going on and you're certain you've done everything else properly, you might want to check that. So I just check it to begin with and make sure that the IMU sample rate is at 832 hertz. That way it matches the float package. Usually the IMU wizard does it, but it's worth just checking because sometimes it doesn't. If you have IMU issues, or it's not riding properly when you're all done, and you're pretty certain you just messed up the IMU calibration, which is possible, here's how I go about doing it over. Do not just immediately go back to the IMU wizard, because in some cases it may just take the default values and then write more values on top of it, and that's not going to help you. What I would do is go to app config, your drop down, IMU, and all your IMU data is here. I would click the three buttons, or tap the three buttons, and go to read default settings, and then write. So that will reset all of that, and it will zero everything out. And when you tap write, all the stuff will be blank, and you can go back and redo the IMU wizard again. However, this seems to be working properly, and so we're not going to do that. I will assume, since the RT data was looking fine, that this went fine and that we can move on to the next step. All right, and now that the IMU is more or less configured, the last couple of steps involve installing the float package and going from there to configure this to respond like you may want it to. And so we are going to scroll all the way to the right, and you'll notice on the top, packages. There are some packages. The one that is relevant to this right now is float. And so you can actually tap, if you don't see this, on the bottom left, you can tap Update Archive, and it will load these. The first one says float, and you will simply go to Install. And this may take a little while, but it's going to download and install that package. All right, install done. Please disconnect and reconnect to apply VESC tool GUI updates. So what it's talking about is that there are different tabs at the top that are specific to the float package. And so in order for that to show properly on the app interface, you would want to disconnect and just refresh this and then reconnect. So that way, when it loads, it will then load the menus on top. Now, before we do anything else, we've loaded the float package. What you want to do, if you haven't done it already or you're not certain, is test the foot pads to make sure that they work. The easiest way to look is, now that you have the float package installed, go to App UI, should be very close to the Start menu, and you'll see on the second little bank of information, Float App RT Data, ADC1 and ADC2. They should be essentially 0. And when you press on one side should go above 3 volts. Let that go. The other side should go above 3 volts. And you'll notice that when you do that, the very first heading, Float App State, it's on startup, which means it's starting up. We haven't used it yet. And the switch is your foot pad. So you press 1, switches in half state. You press both, on. That means that this is primed to turn on when it gets level. All right, so this is just making sure that your actual foot pad works. This is the easiest way to see that it works, to see you're registering above 3 volts, and that when you're pressing both, you're registering above 3 volts, and it is reading that. Now, when you first install the float package, the values in it, as far as the balancing is concerned, are usable. They may not be perfect for you, but they are usable. It is writable. However, what we need to do first is something very important, and so we're going to go to float config, and this is going to be your interface for tuning the balance values of the board. So before we do any of that stuff, we're going to set this to the appropriate values for this battery. If you skipped all the way to the back, go back to the front of the video where I talk about battery voltages. The motor values for cutting off the motor were set way down low. And so that is that. What we're going to set here are the specs of the battery for tiltback, which is what VESC refers to as pushback if you're more one wheel inclined. And so we're going to go to the drop down. The default menu is Tune, and we're going to go to Specs. And so disable float package. That's if you need to do motor configuration again or other stuff. It'll keep this from interfering with how the motor operates, but we're not touching that now. Loop hertz, leave that alone. And here we go, voltage tiltbacks. These two are important. High voltage threshold. This is a voltage at which point it will tilt back or give you pushback to signify that you're overcharging the battery. This may happen if you charge the board to full and then you go ride down an incline, and through regen braking you overcharge the battery because you started at full to begin with. And so this will give you that tilt back to warn you that you're overcharging the battery. And so you have to set it for that battery. Generally, I would set that to about 1 to 1.5 volts above full. And so as per what we talked about in the beginning of the video, full for a 20S battery, which is what's in here, is 84 volts. And so I would set my high voltage threshold to 85 volts or 85.5 if I wanted a bit more leeway. Now that is unlikely to severely damage your battery, and so that's what we're going to put it at. If you're afraid of severely damaging your battery in such a condition, you can set it to 85 volts, which over the spread of 20 groups is going to be just fine. And so that's what I've set. If you have an 18S battery, you would do 75.6 as full, and so we would do 76.6 volts for the high voltage threshold, for example. For other S counts, series counts, I'll have that in the description below, in the same place as all the other values that I'm not going to specify here. And it's really just a matter of taking your full voltage and adding a volt on top of that. And now the other important one, low voltage threshold. This is the tiltback or pushback to signify that your battery is empty. And the empty value we're going to use is empty regular, not empty empty. So 3 volts per cell is a very good way or place to look at your empty battery voltage for tiltback or pushback. And so 20S battery in here, 3 volts per cell. And so we're going to set this to 60 volts. Okay? So 60 volts is going to be what this considers empty. And that is empty regular. If this were an 18S battery, so if you have a build similar to this, but you're using one of my meat packs or a Z battery torque pack, or you used a stock GT battery in a DIY build conversion type thing. So if you have an 18S battery, your low voltage threshold would likely be 54 volts. And you can figure that out by just taking 3 volts per cell, multiplying it by your series count, which was explained in the beginning of the video. And I'll have other values written down in a link in the description somewhere. And so we have now high voltage threshold. This is a 20S battery. High is 85 volts. So that way, if I overcharge this going downhill, it'll signal that. Low voltage threshold, 60 volts, it will signal that. The rest of this, you can just leave it alone. So we'll hit right. And that is the specs of this. So we now have low voltage tiltback set. The low voltage for cutting off the motor is way down low, below what we'd ever would get to normally. And so now we can get to the rest of this stuff. Fortunately, this will work pretty much as is. And you can test that. It's probably better to test it on the floor. I'm going to get my gloves and test it on the bench. The reason I get my gloves is because if it behaves a bit oddly, I don't want the grip tape to shear off all my skin, because then I can't build anything anymore. So there we go. So it should just work. All right, so it's functioning. So that's fine. So that's good. At this point, if you wanted to, you could stand on it and test it that way.
Surf.0 has added a hand test feature in Float Package, so this enables you to test the board with your hands without the risk of a full power runaway if something was done wrong.
Now, at this point, it's pretty much functional. It can be written. It might not be the ride feel that you like, but the default tune in Float Package, after you set the specs up with the voltages and all that, it's writable. It can be written and it'll function. And so you can then adjust the values under tune and tune modifier in order to tailor the ride feel to what you prefer. You can try other people's tunes. I'm sure on the pev.dev forum and on the Facebook groups, people will share their tune settings and can create more of a ride feel that works for you. I only changed a couple of things and I'll just do that now, but this is rideable as is, and then you would further test it on the ground by standing on it very carefully. And so if this is your first time setting something up, I would leave the default tune as it is and test it first to make sure that it is functioning the way you expect it to, that it's responding to your lean and all that stuff the way it normally would. And you would do that by just placing it on the floor, making sure you're in a relatively safe area, and holding onto something nearby just in case it's a bit wonky, or just go outside and try it in a safe area, the sidewalk or something, just to make sure that it functions normally. So assuming that it does, which it seems to, I'm just going to go ahead and change a few values. And so I set angle P to 26. I set rate P to 0.80. I set angle I to 0.02. I limit stays the same. Mahoney KP I lower to 1.8, and that all stays the same. Hit right. All right, and then we'll drop down and go to ATR. I like having ATR on, but I usually bring the ATR strength down to like 0.9, and that's about it, right? And then the rest of it I kind of just leave the same. That's about all I do. And so at this point, it should be rideable. It should be functional. I'm going to go ahead and just take it outside and give it a quick go. And then that should be it. If it's not riding normally, as in it's not functioning like a balanced skateboard would function, then chances are you may have messed up the IMU calibration. If the motor's doing all kinds of crazy stuff and it's crunching and screaming and doing all weird stuff, you might need to redo motor detection and make sure that you're following the values that are linked below and are on the forums. But this should help you get a functioning, relatively decently riding board until you then adjust the tune to suit your preferences. And so that's about it. I hope that this was helpful. I hope it sort of brought some of the VESC setup a little bit lower to the ground for you. And thank you for watching.